All right. Hello, everybody. My name is Alex Bates. I'm a staff scientist at Sandia National Lab. I work in Sandia's battery abuse testing lab, where we do all the fun stuff like blowing up these new up and coming batteries. Sorry, Robert. Let's see. I'll turn my camera off so I'm not blocking the screen, and we'll move on. So just a little background on Sandia National Labs. We have two primary facilities. One, we can do up to 1 kilowatt hour of testing. The other, we can do up to 100 kilowatt hour of testing. So the left images is that smaller one. So we're talking about single cells and small packs. And the right one is the larger one. And in there, we're talking about large packs. Oh, sorry about that. Okay, it should be coming through now. All right. So again, left image is the smaller packs and single cells. Right image is the larger packs and even up to rack scale. Within both of these facilities, we can do pretty much any type of abusive condition you can think of. We're an R&D lab at heart, so we do off-normal things like laser initiation of thermal runaway. The bottom right is some of our battery calorimeters. We can do material scale all the way through large pouch cells on the order of 20 amp hours within those calorimeters. I'll skip this just to save time. I do have some fun videos later, so no worries there. This slide is just to demonstrate that Sandia does do work from material scale all the way through outreach codes and standards. A colleague of mine has co-authored the USABC Safety Testing Manual, which is used quite frequently, at least here in the US. Material scale is something that we're kind of pioneering some groundwork on. Material scale safety is important for a variety of reasons, which I'll get into a little bit later. We also pair a lot with our fire sciences folks for simulations and modeling. As you can imagine, safety testing is quite expensive, so we like to get out of it what we can. So why is sodium ion safety? Sodium ion, as you all probably know, has kind of emerged as this new up and comer, at least in the commercial space. It's got similar lithium ion performance, probably a little bit lower than you would like, but similar. And it's got similar fabrication requirements. And the big benefit is the potential for lower materials costs. Now you'll see a lot of sodium ion startup companies advertising, but the safety is still largely unknown. At least that's what we think here at Sandia. We like to get our hands on cells and put them through the ringer ourselves to validate that safety. And as you can see in that right image, the safety of the particular cells that we received and tested was definitely somewhat questionable. So for this presentation, I'm going to show 1.5 amp hour sodium ion 18650s. These are cells that we purchased commercially overseas. And I'm going to compare that with 1.5 amp hour lithium ion NMC 18650s. Those were also commercially purchased. And then the second part of the presentation, I'll give an introduction to Sandia's material scale analysis. As you all probably know, there is a sodium ion grid installation in China on the order of 10 megawatt hours with plans to expand that up to 100 megawatt hours. I've also seen some discussion of, I think, CATL bringing a grid infrastructure or a grid scale battery to market, and there's probably a couple other companies out there. So let's move right into the destructive testing. So these are the cells that Sandia got a hold of. These are called Hecate cells. They're pretty prevalent these days. You can find them quite widely. I was looking recently for some other types of sodium ion cells to see if we could procure some. There is a wide variety of different, I want to say, distributors. It's hard to tell if the actual manufacturer is different, but they're certainly available from a wide range of vendors now, which is markedly different from just 6 months ago. We did experimentally test these cells. We got 1.43 amp hours, so pretty close to the rated 1.5 amp hours. We also did materials characterization, and we found these to be nickel manganese iron, 111 composition. We found the anode to be hard carbon, which is pretty typical. The salt is a NaPF6, and then the solvent is an arrangement of different organic solvents that you would typically see in lithium ion batteries. This table here is not exhaustive by any extent, but just to demonstrate some of the different sodium ion chemistries or configurations that there are around the world.